Hey, Kevin. Did you get a chance to go through Wix Theorem?
Yeah, I did. And I caught, I think, just like some minor typos.
Oh,
I think that you might care to know about.
yeah, please. Yeah, just send me an email so I have a record of it.
Okay, cool.
But yeah, that's great. I really appreciate that.
Yeah, maybe just like a dropped index here or there.
Okay. Yeah, easy to do.
Yeah, for sure. Yeah, just like page 213, I think. I highlighted it. Why? Oh.
Let's see, 213. Okay.
Yeah, I guess I had a question. Maybe this wasn't a typo. This one, I wasn't sure if it was or not.
Okay.
It's the first line of the sequence of equations at the bottom of page 213.
Okay.
And in that parentheses on the first right-hand side, we have all the indices are ordered 2, 3, except for the second term.
2, 3. Let's see. Are we in section 9.5? I'm wondering if we're looking at the same version here.
Yeah, I believe so. I screenshot it on my phone, so let me go ahead and open it on my computer and make sure I'm in the right spot. But I'm seeing bottom of page 213.
I don't see any trees, so
okay, just a second here. And this is PD. This is the actual book page 213, not PDF 213. If there's a difference.
okay. Hi, Lon.
No difference.
Let's see.
Yeah, opening the current section. Yes, section 9.71.
Oh, 9.71. Okay, that's I've added something somewhere. So 9.71. Got it.
It is. Let's see. So about a page worth into it, we'll start a sequence that starts with phi 1 hat minus times the ordering of phi 2 and phi 3.
Yeah.
And then on the right-hand side there, we have 4 terms in parentheses.
Mm-hmm.
And they're all 2, 3 index, except for the second one. I'm wondering if that's an accident.
Let's see.
Because
yeah, all right. No, that's not. That's actually what I'm multiplying is phi 1 minus times the normal ordering of phi 2, phi 3, which allows me to put phi 2 minus to the right of phi 3 plus. So the term in parentheses is normal ordered. All the minuses are to the right.
Okay. I do see that all the minuses are to the right. I had just...
Yeah, so let's see.
Oh, I see. Okay, so the middle 2 terms are sort of conjugate in some sort of way.
So yeah, to normal order 2, 3, we've had to commute phi 3 plus and phi 2 minus.
I see. Okay, so no typo there.
No, yeah. No, that one's correct.
Right, I believe it.
I'm sure there are typos, but yeah.
That was one I wasn't sure about, but I think like let's see if I can see something that I am sure about. Yeah, right up in the equations, right above it, I feel like we're missing an index 1 on that phi minus in the last right-hand side.
Yep, there's a 1 missing. Pretty sure that's the 1. Yeah, okay. Here, let me pull up the, let's see, where are we here? Let's see, so.
That's probably, if I see others.
Yeah, let's see. Yeah, I can catch that one now. Well, we're still waiting. Has anyone seen Tyler or Alex lately?
Haven't seen anybody lately.
Yeah, right. I
I
hear
saw
you.
her Friday, but that's about it. She could have just
Yeah. She
became a
wasn't.
hitchhiker. Okay.
She wasn't in quantum this morning. Let's see. So 5.7.1. Ah, there it is. Okay. Yeah. Well, I got the one subscripts on those, so those will be there next iteration. Yeah, all right, got them. But yeah, rather than hunting things down during class, let's in general we should it's best if you just email me. Now let's see, wait a minute. There we are. So we were talking about Wix theorem, and Kevin found some typos, but in general, if you find any typos, please just send me an email, being as specific as you can as to where they are, and I will catch up with them in due course. So I had asked you to look at these examples of Wix theorem. Are there any questions on Wix theorem? Basically what we have to do is get all of the annihilation operators in any product of fields. We need to get all the annihilation operators to the right. And that involves commutations. Each time we commute a pair of fields, it's a propagator, which is just a function, so we can pull the functions out. Then I do an iterative argument. I won't quite call it a proof. You could add some formality to it, I think. But what happens is pretty clear. I do the examples of 2, 3, and 4 fields, and I think you can see what's happening. If we make the an application to n fields, what we're always going to get is something like band structure in atoms. Let's see, no, not band structure. Once we normal order any product, we're going to have, see, now how did I label these things? A normal ordered product of a bunch of fields up to some 5K times a bunch of Ds, and those each have 2 indices. I'll just call it CD, where, okay, the principal property here is that each field index, so these run up, let's say, from 1 to n. Each field index, 1, 2, 3, up to n, occurs exactly once. All right, we never add or subtract any field indices. So if these are 1 through k, then this will be, these will include k plus 1 up through n in some order. Now, the argument of Wix theorem is that those occur in every possible ordering. So if this has k fields left, then we're going to sum over all possible k, but we're only going to be taking out 2 at once. So the cases are a little different for k even and odd, but the claim of the theorem is that you have a sum of terms like this over each possible k. So if you're starting with phi 1 through phi n here, then you're going to have a term where they're all normal ordered, because after all, that's the goal. So they're completely normal ordered. Then there are going to be some terms that get normal ordered but have 1 D left. So you'll have normal ordered products that have n-2 fields and a D. But that happens if I bring in one field, I have to commute the minus all the way through, which means that yeah, no, sorry, I'm getting ahead of myself. Let me try and state the form first, and then argue that that's really the form that has to happen. You're going to have every possible D here, because in bringing a phi minus through, it's going to have to pass each of the other n fields. So you're going to have things with 1D, you're going to have things with 2Ds. This is going to be what, n minus k over 2Ds. And all the way down, so if n is even, then you'll end up with something that has just Ds and no normal ordered products. So you'll have n over 2 of these. And the statement of Wix theorem is that these occur in every possible combination. So you get every distinct pair. So if we have, say, 4, you're going to have a D 1, 2, and then the other has to be 3, 4. And you'll have a D 1, 3. Each possible combination here with a D 2, 4 left, and then D 1, 4 with a D 2, 3. So each possible pairing is going to occur exactly once. And to see that that's really what has to happen, let's suppose it's true. Let's suppose that at each order k, we have a sum of terms where these pairs range over every possibility exactly once. Now we're going to do an iterative proof here, proof by induction. Now bring in one more phi. So phi, let's bring in phi m here. Okay, then what's going to happen on, say, the kth term? So we've got phi m coming in, and at the kth level, we have k fields here, and then we have d possible d's. It's the phi minus that's going to give us something. And in order to be normal ordered, this phi minus has to get all the way over to the right. And each of these fields has a phi plus in it. So each time you pass one of these, you're going to get a d. So you're going to end up with a d m1. And now that's a function, so you don't do anymore. Once you've got it past there, so let's see, what do you do with this first one? You can write this as phi 1 phi m plus the commutator phi m phi 1. And this is a d m1. So you're going to get two terms just getting past this first one. You get a new d corresponding to the 1 and the m. And you get the phi m 1 unit to the right. Now you got to pass phi 2. So this term is going to end up being phi 1. Then you'll have phi 2 phi m plus d2m, plus this term. So this has added 1d to this list. Now notice that as you move phi m through, it's going to have to pass each one of these exactly once. So these successive terms have phi m moving step by step through the list. And each time you do that, you get the corresponding d. So you're adding exactly phi 1m, phi 2m, up to phi km to this list of d's. These d's that we add cannot have been in this list because M was not in the list. Each index occurred once already, and there was no M. We bring in a new one. So bringing this in, we produce a new list that has the normal ordered set, phi 1 through phi k and phi m. So eventually we get it through with a list of all the Ds we had, plus a new list where we have k minus 1 fields, and we have D M S, let's say, with all the old Ds. So we have one more D than we had and one fewer field when we bring that one in. And there's one of these for each possible S. So what happens bringing a new field through is you create exactly one of each possible commutator at each level of this hierarchy. And the net result is you end up with the form I described in the first place, where every possible arrangement of Ds occurs with every complementary set of fields. And again, every line always has each index exactly once. So the importance of this for us is that we're going to be taking vacuum expectation values of this whole thing. Bah! Except the vacuum expectation value of any normal ordered set of fields is 0. It's got annihilation operators over on the right. So in our vacuum expectation value, all of these terms vanish except the last one. And it's not hard to write the last one. I mean, it would be hard if you had 17 fields, but it's not hard if you've got 6 or 8 fields. You can write all the products of 4 Ds if you've got 8 fields. It's
normal ordering of like annihilators on the right side. If you have chosen the opposite convention, the same thing would have occurred. Is that correct?
Well, with the annihilation operators on the left, now they act to the left the way their adjoints act to the right. On a vacuum state, that's going to create particles. So no, it would not annihilate. You need the annihilation operators to act to the right on a vacuum state, or to the left on, well, let's see, acting to the left, they look like creation operators. Right, so all I'm saying is that, you know, a dagger acting on the vacuum, or sorry, A acting to the left is dual to a dagger acting to the right, which is a 1 state. So this is equivalent to a 1 particle state over on the left end.
Could that have been fixed with like a reverse Wix theorem, where you kind of like try to go the opposite way?
Oh, you could certainly have moved them through and you get a corresponding theorem. Yes, that's true. That's true. Yeah.
I just want to make sure that that whole convention of left or right was kind of ambiguous and we could have chosen. But as long as it's consistent, it's fine.
Yeah. I mean, yeah, you could have, let's see. So, well, we would get the same result if we moved all the pluses to the left, but we could move all the minuses to the right and we would get a similar theorem, except the normal ordered bits would not vanish in the vacuum state. And that's the goal we're really after. Do you see that?
Yeah, I understand that. Yeah. I understand what you're saying. Yeah, for sure.
Okay, all right. But yeah, there's that kind of symmetry. I think that's what you're asking about. So are we good with Wix theorem? Shall we move on? Okay. All right. So let's, yeah, we're going to draw a Feynman diagram. What we're interested in then is vacuum expectation values of products of fields. So the thing we're trying to evaluate is this, we had incoming and incoming particles, outgoing particles. We want this transition amplitude. We saw that we could write this as sums and products of, what do we have? We had products of a bunch of wave operators like this. We had exponentials, a sum of a bunch of exponentials like this. I don't. This is in the notes, and we're going to be writing this thing again eventually. But various factors here and normalizations. But then we get a vacuum expectation value of the time-ordered product of a bunch of field operators. And then we get the interaction Hamiltonian. Like this, possibly integrated depending on the Hamiltonian. But this is the thing now that we want to evaluate. And the argument that we now made is that we can replace this whole thing, including any one term in the interaction Hamiltonian. Remember, those arise as products of fields as well. So we just have some product of fields here. So phi1, phi2 to phi k, and then say our interaction Hamiltonian is something like phi to the fourth, right? So we have a Klein-Gordon equation plus an interaction between foursomes of fields. Then at first order, you expand this exponential and you're going to have a phi to the fourth here. Vacuum expectation value of time ordered product like this. And what we do with this is now we use Wix Theorem to replace this as a sum of products of propagators. D3, 4, up to D. Let's see, we have K plus 4 here. So K plus 3, K plus 4 as one example of the products of fields that occur here. But we get every possible combination here once. So what does this describe? Well, let's start with just two fields. So we have the vacuum expectation value of the time ordered product of phi1 with phi2 and 0. Well, we can write this as a normal ordered product, whatever order these are in. We can replace it by a normal ordered product plus a D1, 2. And replacing that, then the normal ordered product phi1, phi2 is going to be 0 plus a function, D1, 2. Now that's a green function. If this field is at position X and this field is at position Y, this is going to be D1 at X minus Y. Getting a call from Palmdale, California. I don't know anybody in Palmdale, California. All right, so we've reduced the field product to a function. Now, what does this describe? We can draw a diagram corresponding to that, and it's simply this. So basically, X goes to Y, and we have a propagator corresponding to that line going from X to Y. and those will go off to infinity. But this is the mnemonic picture that we're going to draw for these propagators. Now, suppose we have a pair of particles. Suppose we have, let's see, 4 fields. If we have 4 fields in here, phi1, phi2, phi3, phi4. Okay, there actually are 3 possible scenarios that correspond to that. And not all of them are actually going to occur in a given experimental setup. So, you know, if our initial fields are, say, phi of x1 and phi of x2, and our final field, so we have 2 fields going into 2 fields. 2 particles coming in, 2 particles going out. Now, this depends on that initial state, right? We started with the expectation value where we had, I think, m particles coming in and n particles going out. So suppose it's 2 and 2. Then what we have is the y's, I'm using the y's here to denote the outgoing particles, the x's to denote the ingoing particles. So this expectation value, let's put it in here, time-ordered product of those guys, we now know by Wix theorem can be written as d12, d34 plus d13, d24 plus d14, d, what's left, 23. Well, which of these can occur, right? So we have 1 and 2 coming in, so we don't have 1 going to 2. So this one doesn't occur. We can have 1 go to 3 or 1 go to 4. So there are 2 possible pictures we can draw here. We can have 1 go to y1, so d y1 minus y. Here, let me make these numbers match. So call this 3 and 4. So this would simply be d13, and this would be d24. Or we could have right. That's this term in the Wick product. Or we could have this diagram where phi x1 links to 1, 4. So we've got phi y4 here, phi y3 here, phi x2 here. So this links 1, 4, and then x2, these don't interact, links to 3. So we get a 2, 3 link and a 1, 4 link. This one can't occur because it's linking the initial particles going to one another, the final particles going to one another. So corresponding to each term in the sum that is the expectation value we're after, that was a phi 4 vacuum expectation, corresponding to each of those terms that can actually happen given our particular experimental setup, we have a diagram. And by using these diagrams as a mnemonic for which propagators to write, we're going to enable ourselves to write down a set of rules that tell us what terms to write in this complicated transition amplitude. So all of this is a mnemonic to help us remember what things to write when we expand this transition amplitude. And it's going to amount to a bunch of propagators, but that there will be other terms, and we need to keep going with examples to see what those other terms are. Wow, Yeah, you know, I'm suddenly thinking it's too bad that Alex and Tyler aren't here because, you know, we're actually starting Feynman diagrams here. But I hope they're okay. And Eli, where's Eli today? Eli was not well last week. I'm a little worried about him. Well, it's recorded. They can watch it. Now let's look at a 5/4 integral. Does anybody have any questions so far? You guys with me here? Okay, good. So
These all can be the same field, right? Or are
yeah,
they different?
yeah. For what we're doing now for a while, we're only talking about Klein-Gordon fields. These, yeah, this is all the evolution of well, multi-particle states, but they're all the same kind of particle. They're all bosons. We can have as many as we want, so no problem there. You know, we'll graduate to fermions pretty soon. But let's suppose we have one of two interactions I want to consider, phi cubed or phi to the fourth. So our Hamiltonian is going to be something like, well, let's see, we have, what does the Hamiltonian look like? Let me write the action. So we've basically got, what's the best way to write this? Here, let's make it simple. So this is our basic unperturbed, our free field. And we're going to add something like lambda over 4 factorial phi to the fourth. I think I've put an I in there. Oh, well, there ends up being an I in there, but not yet. The 4 factorial is simply because this is an interaction. This is something that happens in the middle of the diagram. And that happens at some independent point, but it by involving 4 fields at essentially the same point, we can interchange these guys freely. And so we're going to get 4 factorial different orderings of those 4 fields, and it doesn't matter. So that'll just keep our normalization. So if our Hamiltonian is has this interaction term, then our vacuum field, let's suppose we have 2 particles coming in, phi 1 and phi 2, and phi 3 and phi 4 going out. So yeah, always this initial and final picture, 2 in, 2 out, and we'll call them 1, 2, and 3, 4. And then we have e to the minus I over h bar times the Hamiltonian, which is now lambda over 4 factorial. This is the interaction Hamiltonian, phi to the fourth. So we would like to evaluate this matrix element, and we're going to assume that lambda is small enough that it makes sense to do this perturbatively. Now, let's see, we worked through the interaction picture, right? So, the interaction picture also works for the interaction Hamiltonian. So if we have lambda over 4 factorial phi to the fourth, then, all right, that's in the Hamiltonian minus I over h bar in the exponential. So, no, sorry. What I want is, sorry, interaction Hamiltonian. All right, the interaction Hamiltonian is this, remember, times the free particle Hamiltonian time evolution. So h0t here, e to the minus I over h bar times h0t here. But what we can do is insert identities. So this is lambda over 4 factorial. So this is what we call the interaction Hamiltonian. That's what goes in the exponent. But now if I write e to the I over h bar, free Hamiltonian times time times one of the phi's, and then I introduce an identity here written as a product of these, you can see that by doing that, and then we have the next phi and so on, we're going to be able to identify this as a product of 4 interaction fields, phi I to the 4th. All right, so we can, by working with the interaction Hamiltonian and that Hamiltonian being comprised of products of fields, we can always replace those fields with the interaction fields. And now, when we do the Wick formulation on this expectation value, all of these are interaction representation fields. So what we get, let's see here, try and squeeze it in over here, is well, we can try the first order expression. All right, the first order expression, we're going to expand this exponential, h bar lambda over 4 factorial phi I to the 4th. We expand as the identity minus I lambda over h bar 4 factorial phi I to the 4th plus higher order terms. That's a squared over 2 factorial and so on. Now we evaluate all of this, and I think we should probably just step through this in detail. The thing we're after is this PQ transition, and the first term in this Taylor series is just the 1. So the first term we get is, let's see, we're looking at, how did I write this? Yeah. So if we have final momenta P1 and P2, and then the interaction is this part of the scattering matrix that's not the identity. And let's say we have incoming momenta. I think I called these Q, no, call them K, K1 and K2. So 2 particles in, 2 particles out. We specify their momentum. And in fact, we're going to do the whole calculation in momentum space, which means we pretty much transform everything in this list. So we have a normalization I z square root of z. And that happens, well, n plus m times. In fact, we have 4 of those this time. Then we have a product j equals 1 to n, well, 1 to 2. And we have the integrals over all the coordinates d4 yi or yj, and then we have a product over all the let's see, well, I don't know which of these is ingoing and which is outgoing, but xi over all the ingoing and outgoing particles. We're going to integrate over all the positions of all the particles. Then we have exponentials. And again, I have to think how to write this. So we have e to the I sum I equals 1 to 2 pi dot yi plus I, the sum j equals 1 to 2 ki dot x, well, j, I or j would work there, either one's fine. But we have a simple exponential in each of the incoming momenta times positions. Then we have a product. Now, what we have are wave operators. In fact, an integration by parts lets us let those wave operators act on the corresponding momenta. I'll go ahead and write it here as a wave operator. Plus m squared, product over I, product over j, box j plus m squared. They're all the same mass because they are all the same particle. And then we have our vacuum expectation value here, p phi's, and the interaction in that. Sorry, let's write it carefully. Time ordered product of phi 1, phi 2, phi 3, phi 4 times our series 1 minus I lambda over 4 factorial h bar is 1, phi to the 4th, and so on. Vacuum expectation. Okay, so this is the thing we're going to evaluate term by term. Now, because we're working with the Fourier transforms of everything, okay, so we're going to have something like a D13, D24 will be one of the terms that we get if 1, 2 come in and 3, 4 go out. Good. Yeah, it is. I mean, that's why there are Feynman rules, right? You know, I'm going to work through this in, gritty detail. Apologies. But the things we want to notice are the regularities of the calculation, because we're going to extract Feynman rules that are going to let us short circuit a bunch of the steps, right? So I'm going to go ahead and bore you, right? You can see it is straightforward. It is just putting the right things into the next step. And computers do that these days, right? Now let's see, for these wave operators, right? We've got integrals over all the x's and y's, and these derivatives, if you integrate these by parts, these are going to pull down pi squared and ki squared, probably with a factor of I. So we can pull out an overall I and from each an overall minus sign from each of these. We have 2 particles in and 2 particles out. The minus signs go away. But
I have a question.
basically, we're under, this is a D'Alembert with respect to P1 or P2. I can integrate by parts and pull down I P1, so I'm going to get a minus PI.
I have a question.
Squared, yes.
In the notes, you're doing a product over n and m particles.
Yeah. So on what I'm writing on the board, I'm setting n and m equal to 2.
Because there's it's a 2 particle scattering. Is that it, or 2 particle interaction?
Yeah, two in, 2 out.
Thank you very much.
Yeah. So the picture that I drew here, but now there's going to be an interaction, right? And well, soon there's going to be an interaction. Let's see. Yeah. So I'm just getting these factors right. So we can write this as minus pi squared plus m squared minus ki squared plus m squared summed over all the particles. So we're going to have a product of each of these. And what we're going to see, well, let me not jump ahead. Best to just press through it. Let's see. Yeah, another way to think of that is that on the legs, once you're out of the interaction region, these become free fields, and so you could let these guys act on those. The other thing that's coming in here are propagators. So if we have a particle at x going into a particle of y, at y we have a d of x minus y, and as a Fourier transform, we have 2 pi to the, 2 pi to the 4th. We're putting the whole normalization here. And we're doing it that way because that makes our Feynman rules easier to remember. We have a factor of I, and then we have k squared minus m squared plus I epsilon. The I epsilon is just a reminder here. And then we have the exponential, e to the, let's see, minus I k dot x minus y. So there. Okay, so our propagators are going to look like this. And so we're going to write them this way. So we have a whole bunch more integrals that we're introducing for each propagator. Well, at 0th order, there are going to be 2 propagators. There will be 2 factors like this. When we bring in an interaction, now we have 8, so there are going to be 4 propagators. So we'll have 4 factors looking like this. Okay, so now, what do we do? Let's evaluate this thing. Yeah, we expand the Hamiltonian term by term. And the time ordering, in the end, the time ordering is going to go away because, right, oh, no, there's a point with the time ordering of the Hamiltonian factors is included under this time ordering. So we don't need to write another time ordering here. The whole thing is time ordering. And that's all going to go away anyway. So let's look at the first term. At the first term, we know that we can write the product, whatever order these occur in with the time ordering, we can write it as normal ordered products which go away, plus a d. Now we have particles 1, 2 going to particles 3, 4. So we don't have a 1, 2. We have a 1, 3 and a d 2, 4. And we have a d 1, 4, d 2, 3. Well, those are the diagrams I drew before, and we're not seeing any interaction yet. Okay, so we have 2 Feynman diagrams to evaluate here. And we are going to do some tricks to evaluate these integrals. So let me see, what do we have? Do I want to write this out? I don't really want to write this all out quite yet. So we have dx's and dy's. dx 2 to the 4th, dy 1 to the 4th, dy 2 to the 4th. Then we have exponentials, e to the I. I think some of those should have been negative. Yeah, let's take the incoming k is negative. So here we have p1 dot x1 plus p2 dot x2 minus k1 dot y1 minus k2 dot y2. And then let's do the first case here, d1, 3, d2, 4. Each of these also has 4 integrals in it. Now, basically going to, well, it's not quite center of mass coordinates, but it's sum and difference coordinates. So we're going to define x to be a half of x1 plus x2, and little x to be, and then just the difference coordinate, x1 minus x2. Okay, this is now for the outgoing particles, and we'll also have a capital Y and lowercase y defined in the same way. So we go to these coordinates, and these integrals aren't too bad. Now, where have I got it? Okay, notice that there's an exponential k dot x, k dot y. There's going to be a p dot x, p dot y. Now, wait a minute. I have to think a second. Yeah, I have to worry about what this k is an integration variable on the Fourier transform here. That's a whole different k. Yeah, okay. In the notes, I've called those q's. Let me do that. Let me call this a q, so we don't confuse it with our p's and k's. So let's see. We've got two of these. That's 8 integrals. Then here we have another 16 integrals, and I don't know. That's probably enough for now. But the nice thing is that most of these integrals are not the q's, but the integrals over the x's and y's are just over exponentials. We have an exponential contribution here, and then these exponential contributions, these are going to give Dirac delta functions. So when we write this factor, p1 dot x1 plus p2 dot x2, I can write x1 and x2. Oh, let's see. How do we get at those? If I take 2 times capital X and add that to little x and divide by 2, that's going to give me x1. And to solve for x2, I just take the difference. So I take, I'm going to have x, capital X minus little x over 2. So I can replace all the x1 and x2 by these things. So I have a p1 dotted in, right? X1 is capital X plus little x over 2, and p2 is capital X minus little x over 2. And now, let's see, we want to do a similar substitution here. The exponential in D13 is going to be e to the minus I, let me call it Q1 X, what did I call 2 and 3, 3 and 4? Were 3 and 4 incoming or outgoing? Anybody remember, or were we specific about it?
They were outgoing.
Yeah, I think they were too. 1 and 2 were incoming.
Okay, 1 and 2 are incoming, and all right, 1 and 2 in, 3 and 4 out. And which were X and Y? The P's were going out, so the Y's are out and the X's are in. Yeah, that's to keep track of this. The rules will let us bypass some of this, by the way, but we're not there yet. So here we have a D13, and so 1 is a Y1 coming in, and then minus an X3 going out. We're also going to have an e to the minus IQ2 with a Y2 and an X4. Okay, now the X3 and X4 get replaced by these substitutions. well, yeah, I'd probably call them Y's here, but those get replaced as well. So let's see. Right. So yeah, the Y's get replaced by a capital Y. This will be minus little y over 2. This will be a capital Y plus little y over 2. And then the x's, this will be a capital X plus little x over 2. This will be a capital X minus little x over 2. Now, I suggest writing all this out. Okay, so now you can scan through this whole list and pick off everything proportional to a capital X. And that's going to give you a delta function of the thing it's multiplying by. So let's see if I can do an example here. Yeah, all right, I've got this written out at the bottom of page 225 of the most current version of the notes. Let's see. There's no, okay, Q1, X and Y. Oh, okay. Yeah, all right. Yeah, these differences end up as just lowercase. The capital X goes out of those. That's the reason for that substitution. So what do we get? We also need to worry about these volume elements. All right. So if I look at the X wedge, the little x, and think of them as differential forms, then I'm going to have a half dx1 plus dx2 wedged with dx1 minus dx2. So we get a half. We're going to get a dx1, a minus dx1 wedge dx2 plus dx2 wedge dx1. And, well, I don't know why there's a minus here, but the 2 cancels and we just get dx1 wedge dx2. And that's not what I got last time. Let's see, why did that happen? I wrote it the other way around and I didn't, oh, I see. Yeah, this is just dx wedge dx with a minus sign. So this volume form is equal to that volume form. So basically I can replace dx1, d4x1, d4x2 with the volume element d4 capital X, little x, d4 capital X. Now, what does that do? Let's do the capital X integral. And let's see, we've replaced this exponential with these guys, so we're going to get a P1 plus P2. And let's see, do we get a minus something? No, we get a, doing the d capital X integral, that's half of this, is going to give us a 4-dimensional Dirac delta function in P1 plus P2. That's the only place these goes. These differences end up only depending on the lowercase letters, and that's really the reason for the substitution. It gets it frees up the uppercase and lowercase. Now, I think I have a typo with some of my P's should have been K's in this formula. This is actually tricky to do without carefully writing it all out, which I clearly haven't done here. Let's see, where can I go without really starting over? It may be that the best thing to do is to actually collect all these integrals. Are you guys looking at the text? You know, let's see. Maybe I will just write this out. So let's do these replacements and get the right thing up here. The part we're interested in are the integrals. And the integrals, all right, we have these factors, we have those k squared plus m squared factors. Let's not worry about that right at the moment, but we have integrals over d4 capital X, d4 little x, d4 capital Y, d4 little y. Then we have exponentials. No, wait a minute. We also have d4 q1, d4 q2 from the propagators. Then we have these pure exponentials. I've erased my coding for the in and out stuff. Let me put it over here. 1 and 2 were in with y, and 3 and 4 are out with x. Is that what we said before? Okay, thanks. Then and the p's are out. So we're going to have p1 dot. Okay, so x3 is going to become a capital X plus little x over 2. And then we have P2 with capital X minus little x over 2. Okay, then we have e to the minus I q1 y plus little y over 2 minus I, those are four-dimensional dot products, q2 dot, sorry, k, k2. Dot y minus little y over 2. And then we have propagators. Let's see, we have D13, D24. So we're going to have integral. Oh, we got the integrals already. So e to the, let me see, minus I q1. And let's see, we want this to be, x minus y. We want this to be the difference coordinate. But okay, so these exponentials, gosh, I wonder if I've done this with the wrong mixings. I'll have to check myself on this. Let's see what I've written here. Let me look down to another example to see which way I wrote these with the propagators. Yeah, those all have interactions. So not so clear what the substitution is. All right, well, the way I defined it, this should be the 1, 3. So let's follow that. All right, so that's going to be a y1 minus x3 in that propagator. Then down here we have q1 squared plus m squared, like this. But now this isn't going to be a simple big thing. This is going to be a y plus little y over 2 minus a big X minus little x over 2. And then the last one, yeah, I'm wondering if I've defined these as the right differences, but this is what I defined, so I'm going to write it this way and see where we end up. So another dummy momentum index with its denominator q2 squared plus m squared psi epsilon. Then here we're going to have 2, 4. So that's right. So we need y2 minus x4, and those are going to be the minus ones. So we have a y minus little y over 2 minus a capital X plus little x over 2. Okay, so that's the thing that we're actually trying to integrate here. So now you just integrate one thing at a time until we get through. So when I integrate the capital X, okay, I've got, I'm going to get a del 4 of, it's going to have a P1 in it. And if it's plus here, I'm going to write a plus. If it's minus, I'm going to write a minus. So capital X, I'm going to have a plus P2. Then down here, I get plus Q1. And here I get a plus Q2. So far, so good. If I now integrate over little x, I'm going to get another 4 delta functions. Little x is going to give me a half. And watch, the halves will cancel nicely, however. But I'm going to have a P1 minus P2. And then a little x here with a plus Q1. And a little x here with a minus Q2. And then it's not so clear what we want to do next. So we'll take a step at a time. We've done the capital X. Let's see, can we do the capital Y's? Maybe we can do we can do the Y integrals as well. Let me try it. Del 4. Capital Y is going to give me minus K1, minus K2, minus Q1, minus Q2. And the little y is going to give me, I hope this is right, but let's see. We have a half. We have minus K1 plus K2. Then here, minus Q1 plus Q2. All right, and then we still have D4, Q1, D4, Q2 left. It's not enough integrals. Why am I missing something? dq, okay. For delta functions. Yeah, all right, I'm gonna press ahead with this. So what have we got? Have we integrated all of these exponentials? So we still have the propagator q1 squared plus m squared, q2 squared plus m squared. We still have those factors. So now we integrate over, say, q1. And we still have, okay, so what's q1? Q1, let's see. Now let's integrate over q2 first. So then q2 from this delta function, no, I want to do q1. So q1 is going to be q1 squared, right? Q1 is minus p1 minus p2 minus q1. The minus will square away, so p1 plus p2 plus q1, q2 squared plus m squared. Then we have q2 squared plus m squared. And then this delta function is going to become, right, we have a half p1 minus p2. Q1 has become minus P1 minus P2 minus Q2 minus Q2. And this is nice because the P1 cancels. This is what's supposed to happen. And we get 2P2, can you see? We get 2P2 and 2Q2. So up to sine, let's see, I was, yeah, we're adding this minus Q2 minus P2. So it's P1, this is coming up P2 plus Q2, but the 2 cancels with one of those. So we're left with a delta of P2 plus Q2, basically. Then these two, minus K1 minus K2, right? Q1 was minus these 3. So that's going to become plus P1 plus P2 plus Q2. And then that's weird. Therefore, 1/2 minus K1 plus K2. This would be plus P1 plus P2 plus Q2. And we get 2 of those. There's something wrong that we're not going to fix before the end of class here. We're close. We're close. This is typical. And what happens is this replaces Q2 with P2, with Q2 with minus P2. And that cancels this P2, and we just get a P1 squared plus M squared, which is fine. Then this Q2, that becomes P2 squared. So these propagators become a P1 squared plus M squared and a P2 squared plus M squared, which are going to cancel the factors I didn't write up here from those wave operators. Then what are we left with? We actually are left with 2 delta functions here. So I'm not actually that far off. I'm off by some 2s. But let me jump to the expression in my notes. We have a del 4 of P1 plus P2 and del 4 of K1 plus K2. Right. those are a little odd. Then I've forgotten the 2 pi to the 4th factors from the delta function. Each of these delta functions brought in a 2 pi to the 4th. And each of these propagators has a 1 over 2 pi to the 4th. So most of those canceled, but let's see, then we have a P1 squared plus M squared, P2 squared plus M squared. I think, well, minus, I'm not sure why let's see, oh, those started out with minus, so they should have been minus. But then, well, this is similar to the answer, right? Let me tell you what happens here. In this product, we have P1 squared minus M squared, P2 squared minus M squared, K1 squared minus M squared, and K2 squared. So each incoming and outgoing particle had a wave operator that acted on the free wave. Okay, we end up with two of those factors. Two of those factors actually cancel here and here. And for this case, remember, this is the 0th order term in the scattering. We have two of these left. And they, in fact, are 0 because asymptotically, the wave operator is satisfied. I mean, it's a free wave asymptotically. So those make this whole contribution 0 despite the delta functions. I mean, we can replace P2 with minus P1 or whatnot. There are still delta functions there, but asymptotically, those don't contribute. Those are 0 too. So this matrix element actually gives 0. Probably, let's see. Well, I think we should all read through this one, and I should make sure that I was defining the right sum and difference variables with this. I'm not convinced, but this matrix element does give 0. This corresponds to no scattering. This is that first pair of straight lines that we drew with no interaction. So next time, what day is today? Wednesday, I'll do the first order scattering, and that will involve some actual scattering. So we have 2 particles coming in, then we have a point where there are 4 particles. This is the 5-4 contribution for the interaction. And we'll have the same 2 particles coming in and out. This can happen 2 ways because these can be interchanged. Yeah, I'll calculate that one for you, writing out the details a little more carefully than I was ready to do today. But you see the basic way that these things proceed. This first one is a little weird because it really does give 0. But we'll see some non-trivial result in the next order. And yeah, I'll double check my variables and write out the whole expression for you next time. So questions about it?
Yeah, I have a question, but not necessarily specifically about that. Isn't
fine.
there a problem we're supposed to be working for this?
All right. Let's see. I have asked you to do some of these. Let's see.
So I thought there was going to be another problem that was on par with like the last one.
Yeah. Okay,
terms of
yeah, all right. On the latest version, which is dated, I think, March 31st, at the bottom of page 234, I ask you to work out the second diagram for the first order interaction. No, second order interaction. So yeah, I've got two exercises there asking you to work through two problems like this.
I don't know. I'm looking at the version from March 29th. Is that the correct one?
I'm
The
looking
last
at
one that's
March,
posted on campus.
March 31. Oh, really? Let me look. Let's see. Oh, all right, March 29th. All right, I'm looking at the 31st. Sorry. So let me open this one.
That's all right. And it looks like in this version, maybe it's been corrected in your 31st, but like on page 232, some of the equations are cut off at the bottom. They just kind of like wrap onto the next page.
Okay, all right, well, that's bad. Let me see. 232. Yeah, oh, yeah. All right.
And I don't think that's the only page that does that. I'm just kind of scrubbing through here. Most of them look okay.
Okay, yeah.
And I don't see the problem stated or an exercise even.
Okay.
Is it on page 230?
All right, in the,
That's probably it. Okay. There's two exercises on 230.
230, yeah, there were two, yeah, 230, I asked you to work out two of the two other contributions. So they're parallel to the one I did. There's just some, shuffling of X's and Y's, right? But you come out with a similar thing. Notice if you're looking at the statement of that first exercise for diagram 2, you'll notice there's a 2 pi to the 4th and a Dirac delta that's P1 plus P2 minus K1 minus K2. You always get that, right? You always get one Dirac delta function for overall conservation of momentum. So between the two vacua, momenta are conserved. So we'll find that all these integrals we do end up giving us Dirac delta functions at each vertex that conserve momentum at each vertex as well. So despite the fact that sometimes you're integrating over all momenta, each time there's an interaction, you're conserving momentum. And then that gives overall conservation of momentum. So yeah, dig into those problems a bit. Start trying to write this stuff out carefully. I do recommend Wix, something like that, so you don't have to write all these long things by hand every time. Yeah, you start on these. I'll check these. We'll do another one or two in detail on Wednesday. But these are the kinds of things to master right now. This is really getting at what we want to compute. Now there are going to be more steps. There are some complications when we write the propagator for the well, we're over time. I shouldn't keep. Does anybody have to go immediately? Yeah, you're still here. We're recording. What the hell? Yeah, just let me say one thing. The propagator for the Dirac equation is 1 over the Dirac equation, d slash minus m. But you multiply numerator and denominator by d slash plus m, you get an ordinary p squared plus m squared in the denominator. In the numerator, you have a gamma matrix. So every time you've got fermions coming in, you're going to pick up gamma matrices. And when they interact with photons, there's a gamma matrix in that. So these matrix elements for computing are going to have products of gamma matrices. The other thing we do is this is a probability amplitude. To calculate a scattering differential cross section, you've got to square it. So whatever we get here, we're going to square that before we actually reduce it down to concrete predictions for, say, electron-electron scattering. So, we can say more about this next time. The lowest order scattering for, say, 2 electrons reproduces Coulomb scattering. But we're going to find at next order, there are a bunch of corrections to Coulomb scattering. So, we'll be able to derive those effects in fairly short order. We need to figure out the right way to do electrodynamics. There's a little bit of work to do there. We need to get practice and derive the Feynman rules for these things. But after that, you'll get so you can go through many of the steps of these things pretty directly. As you point out, Lyle, it seems simple enough. It's just keeping track of all the detail.
Yeah, it's rather obvious, right?
Yeah, right. Simple, no problem. A little long, maybe. All right, so I'll see you guys on Wednesday. Thanks for your attention.
I have a small question. It's
Yeah,
related to the G2. I've seen like some science, some people who are science contributors to like the media, and they keep saying that like it's a pretty impactful. I recall you saying that it's a somewhat like a detail-oriented kind of discovery. Could you like talk a little bit about that? It's like how would you as a very strong, I think, theorist, how would you classify this?
Now, what are we talking about? We're talking about the muon dipole moment?
Yeah.
Okay. So this seems to be confirming, this has been sort of in the air for, I don't know, maybe even a couple of decades, that it looked like there was an anomalous contribution or value for the muon magnetic moment. Now, I've seen 2 claims now from a group doing lattice QCD. The muon is heavy enough that the contribution to its dipole moment, right, comes from Feynman diagrams like these, right? You look at everything that can happen. Well, the contribution of the strong interaction is not negligible for the muon magnetic dipole, because the muon's 100 times as massive as the electron, 200 times as massive. So these guys have run supercomputers for 3 months calculating lattice QCD corrections, contributions to the muon dipole moment, anomalous dipole moment, where anomalous just means everything that doesn't come from the lowest order Feynman diagram. And they actually agree with the new result. They claim that their results, their theoretical results for the strong contributions to the dipole moment actually predict this new result. So it may be in agreement with the standard model, and like a lot of hoopla over nothing, right? So based on that, these guys are going to be really disappointed if it goes away, right? They want us 5 sigma, and they've shown that. Now, their calculation pushes the limits of computers. So, they say in their article, well, if we can refine this once computers get better, which is quite an amazing statement given just how much computation is involved. When I think back to the lattice QCD calculations from 40 years ago, you had a grid that had maybe was 6 by 6 by 6 by 6 was all you could handle. I don't know how big the grids these guys are using. They're probably 100 lattice points on the side or something. I don't know, but those results are at about the same stage as the experimental results for the magnetic moment, and it looks like there could be agreement. Now, that said, from a theoretical point of view, this could be a very exciting thing, because it could be if it actually is in disagreement and does indicate the presence of some new particle, one particle it could be is a supersymmetric partner. So I think a great deal of the excitement is that this could be the first direct evidence of supersymmetry. But maybe not. You really have to wait and see with these things, right? Or if you've got some theoretical idea that going to explain it, publish quickly because this could evaporate.
Yeah, I think I saw like some numbers where it's like 40 papers were published on possible contributions.
Yeah,
it's like wow, that's
before this all evaporates, you could see hundreds, right?
Wow.
This is where a lot of people earn their keep, cranking out stuff in response to trying to explain any sort of new result. But there may not actually be a new result here. This could be in agreement with the standard model. But, you take a deep breath, wait and see what happens. If there really is some new thing going on here, it really could be supersymmetry, a supersymmetric, what are they called? Like a leptoquark could do something. Do you know what I mean by that? If you build a unified model of like a grand unified theory, which is, people are not making grand unified theories directly these days, but that's what would emerge at low energy strings, say. But what people were looking at as a first crack at an interaction for quarks and leptons is, matrix elements that would connect the three different colors of quark and the electron and neutrino, the lepton pairs. And what you can do is divide this up and put an SU3 up here and an SU2 down there. So the weak pairs interact via SU2, the quark colors interact via a generator of SU3. And then there's a 1, 1, 1, minus 3 halves minus 3 halves that commutes with both of these. That would be your U1. So you can nest the standard model inside an SU5. And it introduces 6 new particles, sorry. And then, conjugates over here. These are called leptoquarks because, a typical term involving these would be some quark and a leptoquark and a lepton. And that allows direct decay of a quark into a lepton. So that's different. That makes the proton unstable.
Indeed, it does.
So this model actually can't be implemented directly this way because of that, because it predicts proton decay at about half-life of 10 to the 31 years, and it's been measured to be longer than that. So, the simplest implementation of this model is ruled out by experiment. But these guys would be heavy mass, and this is a typical picture of the kind of unification you'd like to see. More likely with E8 or E6 than SU5, because that's what comes from string. But there are string reductions, string compactifications that allow the half-life of the proton to be above 10 to the 35th years. So beyond what has been measured. It's still a testable prediction. But any sort of real unification is likely to involve some sort of leptoquark at some mass level.
I guess the lower temperature symmetry breaking that would also be applied to this kind of idea.
Yeah, Yeah, so these guys get large masses through some spontaneous symmetry breaking. You know, a Higgs type mechanism or something. There are various ways that things acquire mass, and maybe coupling to Higgs automatically gives those things heavy masses. I'm not sure, but the you know, we don't see proton decay yet. So those masses have to be fairly large. But for the muon magnetic moment, if you've got a muon that can emit an X, and you know, maybe it does like a quark anti-quark pair for a while and absorbs it again, absorbs another X and comes off as a muon. This is going to contribute to the magnetic moment.
Okay.
That you mentioned.
I don't know.
So, you know, diagrams like that, there are various things that could happen. So when these guys do these lattice models, they're including maybe not that diagram, but you could do a similar thing, but with the weak interaction. If say this emitted a W or a Z particle, that W or Z can interact with quarks too.
Yeah.
And the contribution of that diagram might significantly alter the prediction for the magnetic moment of the muon. So, you know, we need faster computers or more supercomputer time. I think
that amazes me that even with the current supercomputers, these calculations last months.
Yeah. Right. This was running on multiple supercomputers.
Oh my goodness. Wow.
Yeah, I know. Hey, I wonder, do I have it open here? I might be able to see. I don't know where I have that article. I've saved it somewhere. Well, no, I don't see it open here. I've got it on my other computer, I guess. But you know, if you've, what happens when something like this happens realistically in the theory and experiment community, somebody tries to duplicate the experiment because you need reproducibility, but also theoreticians go wild at times like this. And if you've got some idea what could explain the anomalous result, you quickly publish that idea before the result goes away or is understood some other way. But that's a heartening thing. You know, you've got hundreds of people out there figuring out what might cause this. You know, and well, one of them could be right. You know, or a half dozen of them could be right. So you're actually exploring the theoretical terrain around this idea very thoroughly, and that's what you want to do. You know, you want to look at every possibility that any knowledgeable theorist can think up that might account for this effect. And well, here are all these theorists out there hoping that they've got the right insight, and it really does happen this
when
way.
they do. Because it seems kind of difficult. Like they all have different, or maybe similar, but they all have different ideas of what could attest to this. Do they have to be? So it's so many. So like the question is like, who could be right? But then would they then have to like say, to test this idea, here's a possible experiment? Is that like what you usually would do, or do you just present it out there in the ether?
Well, you present as much as you can as quickly as you can.
Gotcha.
At times like this, but yes, hopefully, a tuning of an experiment, and people on the experimental side are always looking for things to test, right?
Mm-hmm.
So this Fermilab group that has this, I don't know how big this ring is. I've seen pictures of it, but it's pretty big.
Mm-hmm.
I don't know, 30 meters or something. It's large. They would love to have a way tweak the experiment and, do another run that, tests some new facet of the whole thing. There's, a constant search for measurable things that, one can go out and build a device that will measure.
Mhm.
This whole neutrino puzzle from neutrinos from the sun from Davis and Bacall circa 1970, where they saw only a third the number of neutrinos that they expected to see from the sun. And it's an indication of mixing. Well, there have been so many experiments since where they use, boron or beryllium or some metals that are more responsive to different neutrinos, right?
Mhm.
So that they undergo an interaction that would actually test for a muon neutrino instead of an electron neutrino. The original carbon tetrachloride tests that Bacall and Davis did were only sensitive to electron neutrinos. So you build different devices that are sensitive. There's still, neutrino science has come a long way. They've got a neutrino factory now at Fermilab outside of Chicago that is, it produces a neutrino beam that is then detected in North Dakota because it can travel, just a chord through the earth, no problem. And it's sensitive, I think, to different neutrino types, and they've got enough beam strength that they can do some very sophisticated. I forget what they're looking for, but neutrino science has come a long way since those first detections of the solar neutrinos. So could be interesting things coming out of that. But yeah, I wrote a theoretical paper once on gravitational squeezing of light. We were talking about coherent light or coherent states in quantum mechanics, right?
Mhm.
And one trait that laser light has, that most readily produced coherent light has, is that the dimensionless uncertainty in momentum and position are numerically equal. And by passing laser light through crystals, you can alter that. You can squeeze, one of the uncertainties in favor of the other. So you have a large uncertainty in position and a small uncertainty in momentum, or vice versa. They use this in light pipes, right? So you want to get a lot of signals down your fiber optic cable. And what you do is you distinguish them by phase. So you want to divide the cross section into small angles and have a different signal going through each one. So you want a very small uncertainty in the phase at the cost of a fairly large uncertainty in the photon number. You don't care about the photon number, you want the phase squeezed. So they use this squeezed light there. Well, I heard a talk on it and realized that gravity, if you pass coherent light past a black hole, it will become squeezed. The uncertainties will shift. And, I wrote a paper on that and immediately got a query from Caltech asking, well, could LIGO see this? Could that be measured at LIGO? Because they're always looking for things you can use a big device for. And I couldn't figure out. The effect was way too small, but oh well.
I see.
Anyway,
Okay.
yeah. So they want experiments, and theorists want anomalies. So this is all good for everybody's science. Maybe they'll dream up some new tests as a result, and we'll all take one small step forward.
Gotcha. All right. That was helpful, especially that that story you had of what to expect if I ever continue this. That's nice.
Yeah. So there are all sorts of theorists, right? And there are those working in high energy physics who are basically working on the phenomenology. They're very in touch with all of these current experiments and, how you might tune models to see this or that or not see this or that. That's different than string theory. String theory is further from experiment than that. We'll get there. There are a few places where you might be able to test string theory now or in the near future. Remarkably, there are actually some experiments that detect things about quantum gravity. I'm very impressed by these astrophysical measurements that look at light travel time from quasars. And I'm not sure how they know that the production was at the same instant, but if you have a space-time foam version of quantum gravity, then high frequencies will see more of the wiggles of the space-time than low frequencies. And so at some level, you would expect there to be a delay in the arrival of high frequency signals from primordial quasars. And the measurements of such time delays have already ruled out some quantum gravity theories. And
really?
Yeah, and in the not too distant future, actually could really put the damper on a lot of space-time foam ideas. So these things are not actually completely beyond the possibility of measurement, which always amazes me constantly what experimentalists are able to do.
I guess if you want to see like those large, if you want to see those effects of quantum gravity, I guess a prime contender are these like massive astronomical events.
Yeah. And now there are these what are they? Some sort of acoustical waves from the early universe actually let people see before recombination. And I'm not sure what they see, looking for echoes of the Big Bang, basically. And an acoustic wave would probably produce some sort of periodicity in galactic numbers, something like that. But anyway, they're able to detect evidence of these things now, and it gives an independent means of probing dark matter. So I mean, dark matter originated, I don't know, a couple centuries ago, I think, with the anomalous stellar orbits around the Milky Way. And maybe not that long ago, but earlier than one would think. Stars far out around our galaxy or nearby galaxies seem to be orbiting too fast for the visible light.
Right.
So, that is like the first evidence for dark matter, but there are actually a half a dozen different things now that all indicate dark matter is not just that. That effect alone is amplified at larger and larger scales. So if you look at clusters of galaxies or superclusters of galaxies, those would not be bound if there weren't more matter there that we're not seeing. And of course, that's right for theoretical work too. Is it little miniature black holes, or is it this or that? All kinds of theoretical ideas for trying to figure what dark matter is, because it really seems to be there. That I think a big hope is that it also interacts weakly, because then you could detect it in an accelerator. If it doesn't interact weakly, we know it doesn't interact electromagnetically or via the strong interaction, because it would have much more dramatic effects if it did. And it would be bound more tightly to the center of the galaxy if it interacted strongly or electromagnetically. So if it doesn't interact weakly, it's a purely gravitational phenomenon. And maybe it's just an indication that we're working with the wrong theory of gravity.
Right. Interesting. I have another question.
Yeah, sure.
Just what does the Klein-Gordon equation accurate, or I guess describe reasonably? Like what kind of fields or particles?
Well, at larger scales, something like a pion, that's a, let's see, yeah, mesons can act like scalar particles at low enough energies where you're not looking at the individual quarks. There aren't many scalar fields. The Higgs field is
that the only like a fundamental one?
The only fundamental scalar, I think, is really the Higgs.
Okay.
Now if you're doing nuclear physics, then pions create the exchange force between neutrons and protons to a pretty high degree of accuracy.
Oh, okay. I see.
You can do that kind of thing. But yeah, the Higgs, and we actually know what the Higgs potential needs to look like. Yeah, I've seen a potential like that arise theoretically. Just inadvertently looking at something else, that sort of a quadratic plus quartic potential can.
The Mexican hat, is that the one you're
Yeah, the
talking
Mexican
about?
hat, that's right. Yeah, it may be that that's actually a very natural potential to have. In fact, you can argue that, well, any potential is going to look like that half the time, because if you do a Taylor series in powers of the scalar field, a field redefinition can remove like the cubic term,
Wow.
extrema, so the first derivative goes away, and so the first couple of non-trivial terms in the Taylor series are the quadratic and the quartic. And so really any potential might easily look that way. All you need is the right signs in the Taylor series and you can get a Mexican hat.
Yeah.
So maybe that's not too surprising a thing, or, maybe there's something more fundamental that actually leads to exactly that potential.
Mm-hmm.
Now, I have to look back and see where it was I saw that. Because, yeah, just those terms came up in some natural way. It was really cool. But we'll see.
Okay.
There are lots of ideas out there.
Yeah, I realized. Okay. Well, thank you very much for taking my questions.
Yeah. Oh, these are good questions, Guillermo. I'm really happy to chat this way. This is the best when we can, really go into things.
Yeah. Oh, now this is a more general question.
Sure.
Is there like I don't want to say easy, but like, is there like a more, like a little more reasonable way that I can like start getting into like reading these kinds of fields and journals? Because I know there's these things called reviews. Do we also have that for topics?
Yeah. There are what's it called? Nuclear physics. I think Elsevier has. What is the review thing called? There are some wonderful reviews. Let me.
Because it seems like I should be just absorbing all this info just so I can have it in the back of my head.
Yeah, I just I'm trying to think what this. Everybody. Nature does these. Elsevier does these.
And that's what they're called, reviews, just to make sure.
Let's see. Yeah, reviews. There are specifically review journals.
Review journals. Okay.
Reviews.
I've seen those. I don't know. And when I try to read their like about page, it's sort of vague in my eyes. I don't understand. Like, are these actual reviews or is that just their names?
Yeah, let's see. Is it physical review letters? No, those are short reports. There's reviews of modern physics. yeah, it seems to me. I don't know why the name of this journal is escaping me, but yeah, I'll hunt it down and let you know. But yeah, there are excellent review articles. You know, lengthy, detailed, accessible.
Okay. Yeah.
And that there are various dedicated review journals. I'll let you know if I recall this one I'm thinking about. Yeah, seems well. I'm not sure. I forget the name, but there are several of these things, and they're really good.
Okay.
So yeah, look up, any topic you're interested in, and you keep learning about new stuff. It never quits.
Yeah.
But
Yeah, sure.
if you find any recent paper on it, you look at the references, right? And you look up some of those references, and pretty soon somebody's going to refer to a journal article. If that field has been active for any amount of time,
Gotcha.
you're going to hit on a review article that will summarize pretty much everything in the field before the date of its publication, and that'll get you caught up pretty fast.
Okay.
That's a good way.
Sounds good to me.
Yeah. So yeah, good luck with it. Is there anything specific you're looking into right now?
No, not right now. I just wanted to make sure.
Yeah, those
I'm
things
well
exist in abundance and high quality.
All right. Sounds good.
All right. Take care, Guillermo. Good talking with you.
Yes, lovely.
All right. See you.
Bye-bye.